Moving from point A to point B is a vital skill in life that enables us to achieve complex goals in the world. Nothing less is required for leg-to robots acting in the real world, no matter their shape or form. Obtaining good locomotion skills, whether it be stepping, crawling or sliding, is a hard task that requires fast learning, since the main goal is not locomotion itself, but rather completing more difficult tasks later in life. Current methods rely extensively on learning in simulation, followed by transferring the learned behavior to the real robot. The problem with this approach is that it takes a lot of time to obtain a good model for the simulator, while the transferred controller still requires some fine-tuning due to some errors between the simulator and reality, a so-called sim-to-real gap. As a result, approaches like this are mostly useful for learning a single skill on a specific robot for which we have prior knowledge of its shape and form. But what if we don't know the model of the robot? What if we employ robots in the wild and they are damaged? What if the environment requires additional skills to be learned? Is learning even possible? Should we take broken robots back to the lab, analyze them to update their model and learn again in simulation? Should we add additional learning time with every additional skill that is required? In this work, we show a better approach to learning, where we obtain multiple skills at once on several real robots with no prior knowledge. And the best thing is, we achieve this in the real world in less than 50 minutes without the need for a simulator. The skills that we focus on here are rotation in clockwise and anti-clockwise directions and gait, which we measure as absolute displacement. Our controller consists of a network of central pattern generators, also known as CPGs, which are a bio-inspired type of neural network. CPGs are known to be model-agnostic function approximators, which are widely used in robotics. It works as follows. When we focus on the state of these two neurons over time, we see a signal that can be sent to the robot's motors. An interesting way to visualize the behavior of the network is to plot these two signals with respect to each other. The resulting plot shows a trajectory in state space. We start the initial state of the neurons in this location. From here on, the progress of the state in time is provided by the network dynamics. We can visualize these dynamics by adding vectors in our state space that indicate the local derivatives. The vector field is governed by the connections in the CPG network, also known as weights. Conventional methods learn locomotion by optimizing the weights in the network. This means that with every iteration, the vector field changes, resulting in different trajectories. We propose a novel method in which we focus on optimizing the initial state. We start a robot with a CPG network containing random weights and the initial state to see how it behaves in the arena. During learning, we keep the network weights fixed, meaning that the network dynamics remain the same, while we test different initial state values. In total, we test 5 different initial states randomly picked in state space that take 2 minutes each. During each trial, we track the position and orientation of the robot to evaluate the initial states. In addition, we log intermediate CPG states that are visited within a trial and concatenate them into a single vector. We can evaluate many additional states by considering each substate as a possible initial state sample. The trick is to use a rolling window in time to evaluate the behavior of the robot after a given intermediate state of the network. Since our evaluation time is 1 minute, while our trial time is 2, we obtain additional state evaluations every time we sample the CPG states for an additional minute. We call this trick bootstrapping, as we gain many initial state samples by testing during a single trial. In addition to bootstrapping, initial state optimization allows for another trick. As we mentioned before, weight optimization changes network dynamics, resulting in different behaviors of the network itself, whereas our approach does not. This allows for the evaluation of multiple skills at once, since improving a single skill does not change the behavior of another. Parallelization means that we obtain the best initial state from a vector of each individual skill. A cool thing to note is that we select here for 3 different skills, but in practice, you could evaluate more skills in parallel without the cost of extending the learning time. Now, let us see how well initial state optimization went. We show the position as a y trajectory, while a red vector displays the current heading of the robot. As this heading changes, we show the previous heading fading on the semicircle. The resulting behavior speaks for itself. As you can see, we can obtain good locomotion skills in a short amount of time. We test our method on 6 modular robots of various designs with similar results. In the future, our learning method could provide the basis for other types of robots, where we can quickly learn locomotion and extend to more complex tasks.